an introduction to the finite element method and the DG method. First, I will talk a little bit about the finite difference method, and then I will move to the finite element method. And last, I will talk about my favorite method, the DG method. So although the first three sections are not exactly DG, but they will help us build the intuition to understand why DG looks the way it does. So let's consider a simple model problem, which is negative u double prime is equal to f with some directly bounded conditions. U0 is equal to u1 is equal to 0. We actually know how to solve this using elementary methods. But the idea of the finite difference method is to use an approximation of the second derivative. So instead of using u double prime, we'll use a different quotient, which is ux plus h minus 2ux plus ux minus h divided by h squared. And the error term is bounded by a constant times h squared. So this is nothing more than Tyler's approximation. And the finite difference discretization goes as follows. Take your interval 0 to 1, divide it, let's say, into n plus 1 equally spaced subintervals. You can do n if you want to. I'm just doing it for simplicity. And the idea is you can use the previous formula and say that u double prime with a negative xi is equal to negative this quotient, approximately, with an error of h squared. So now, if I take this point x1, I can use the value of u at x0 and the value of u at x2, and I can find an approximation to the second derivative. So now if I look at this, finite difference equation here, I can create a vector UH, and I can drop the error term, and also I can use the boundary conditions to know what UH0 and UHn plus 1 are equal to. So in other words, my UH is a vector UH0 up to UHn plus 1. And this is a set of n equations. And I have two other equations here. So I have n plus 2 equations. Two of them are trivial. And then I can write it in matrix form. And I have a matrix A times a vector U is equal to a vector F. So at the end of the day, you are just solving a linear system. Now, there are multiple properties about this matrix A that makes it very nice. It is symmetric. It is three-diagonal. And also, it has other properties. For example, it is semi-diagonally dominant with this 2 right here. So we know it has a solution and so on and so forth. Furthermore, we can prove that if my function f is in C2, if my function f is in C2, the difference between the solution u and the approximation would be bounded by c times h squared, which is a good bound for most applications. If you have h equals to 100, you would expect the error to, if you have h equals to 1 divided by 100, you expect the error to be on the scale of 1 divided by 10,000 and so on and so forth, okay? Now, I could look at a simple example. Let's say an example where u is equal to sine pi x. And I would look at my approximation UH, and I can look at my function u, and I can see that my approximation is doing a good job with 20 points. Remember that we can make n equal to 1,000,000. It is fine because the system right here is a very simple system and can be solved in O(n) operations because it's three diagonal system. Now you can see, for example, that the error is bigger at the middle, and you can guess why, because the second derivative here would be pi squared sine pi x, so it's bigger, and so on and so forth. Now we could do the same thing in 2 dimensions. I can define the Laplacian operator, delta. Basically, delta u is just uxx plus uyy. And now I can, sorry, this should be a partial. And instead of using just 2 points or 3 points to approximate my u double prime, now we need to use 5 points to approximate the Laplacian, namely the one on the right, the one on the left, the one on top, and the one on the bottom. And now I can do the same thing. I just have a more complicated formula, and they have the same error term, so we can do things in 2 dimensions easily on Cartesian grids like this one. And it's a very popular way to do it, especially in electromagnetics. It's a very well-known method to be robust. Now, question is, what if the domain is not simple? What if it's not just a simple square? Doing the same thing is not going to be easy. The domains that we'd be looking at would look something like this, could be circular like this, and so on and so forth. And this is where the finite element method really shines. Also, what if I wanted something more than OH squared as my error? What if I wanted something like OH cubed, OH to the 4th, and so on and so forth? So let's see what we can do. Let's start with that same ODE. Negative u double prime is equal to f with directly bounded conditions. And let's multiply both sides by a function v and integrate. So what I did, just multiply it by v, and then I integrated. And then let me integrate it by parts and use the fact that u0 is equal to u1 is equal to 0, so the boundary terms would go away. And here's what I have found. I have found that the integral from 0 to 1 of u prime, v prime, is equal to the integral from 0 to 1 of fv. This right-hand side did not change. Those two are the same, and I applied integration by parts to the left-hand side. Now, this is not rigorous at all because I did not make any assumptions on u and v. I just multiplied and integrated, but we can make it more rigorous. But the idea here at the end of the day, I have a bilinear form. It's a bilinear form, AUV is equal to a linear functional in V. And this might remind you a little bit of something like Lax-Milgrom lemma, which is exactly what most people use for problems like this. So let's make it a little more rigorous. We'll define our L2 space to be the space of functions that are square integrable. And we have an inner product on this space, and we have a norm on this space. And then we can define a Sobolev space, HK. And HK is a space that consists of functions U that are in L2. And also, the Zeit derivative is in L2 for all j's from 1 to k. So first derivative is in L2, second derivative is in L2 up to k. And we can also define semi-norm on HK. This is not a norm, just a semi-norm. And if we take the sum of these semi-norms, square them, and take a square root, now this becomes a norm on HK. You notice here that I'm only considering L2 and not LP, but most of the analysis that we do would apply to LP with some small deviations. Also, one more interesting space that we'll be interested in is H01, in which I need my function u to be in H1 and to be 0 on the boundary. And the reason why we want it to be 0 on the boundary, because it was already in the problem. It was u0 is equal to u1 is equal to 0. Okay, so let's go back to Poisson's equation in 1D. So as we have seen before, we had u prime, v prime is equal to fv as an inner product. But now the space that we work with is H01 of the interval 0, 1 for all V's in this space. Okay, so if I read it again, I'm trying to find U in this infinite dimensional space such that AUV is equal to LV for every function V in X. So this function V is called a test function. Okay. And the space in which U lives, we call it a trial space. And as you notice here, the trial space is the same as the test space, but this is just a special case. We could do finite element on spaces that are different. Okay, so what do we know? We know from functional analysis that given f in L2, we actually can relax this condition. But for the time being, let's keep it in L2. If f is in L2, the problem above has a unique solution. Okay, there is a single U in H01. Let's remember that H01 just means that U0 is equal to U1 and U is in H1. And these traces U0 is equal to U1 is taken in the sense of the trace theorem, which should not be very important. You can think of H1 as the space of absolutely continuous functions if you're not comfortable with Sobolev spaces. Okay, so the idea of the Galerkin method that was invented roughly in the 1920s, 1930s by Galerkin is that instead of solving that previous problem of finding U in an infinite dimensional space such that AUV is equal to LV for all V's in X, you pick a finite dimensional space V. And then you solve the following problem. Find U in V such that AUV is equal to LV for all V in capital V. Okay, so the Galerkin method just says the following. I have a weak formulation. I did not actually, this is what we call a weak formulation. I should have mentioned that before. Instead of having a weak formulation on an infinite dimensional space, we just pick a finite dimensional space and solve it. And to make it even easier, if you have a basis on V, it's called Phi or Phi. This problem, this discrete problem, can be written in terms of the spaces using the bilinearity of A. And you end up having a linear system, a very simple linear system, where the entries of A are basically the values of this bilinear form at the basis. There's just one thing special about these V's. If V is a subspace of X, we call this method conformant. Conforming methods are usually the easiest methods to analyze because they inherit all the properties of the bilinear form A. For instance, for Poisson's problem, A would be coercive and symmetric. And what happens to the matrix A, the matrix A will be symmetric positive definite, for instance. So it inherits all the properties of A, not all of them, but the interesting ones. Let's look at a simple Galerkin method, something that we have seen in undergrad, most likely. For example, the Fourier basis, which is basically the span of sine functions, sine j pi x. It's a conforming space. And it can take the following basis. The reason I'm taking this following basis is so the matrix A is the identity, so it's simple. Furthermore, I know something about the error. If f is a C1 function, then the L2 norm of the difference between U and UN is on the order of ON to the negative 2.5. And we can talk later about why it's negative 2.5. So if I look at this approximation, it is fine. I could, for example, take my function e to the x and look at a plot of the error, and you could see that the error actually behaves like Cn to negative 2.5. It could be that the error would decay to 0 faster under some assumptions about the function f, namely if the function f is 0 both endpoints, it would be faster, but there's no reason to expect anything faster than n to negative 2.5. Now, for most purposes, if you're solving something like this is going to be nice because you're going to get an error of 10 to negative 5. If this is what you're looking for, this is fine. Let's see another basis. I'm sorry. Let's take the space of polynomials. Pm is the polynomials of degree at most m. And let's take the intersection with h01. In other words, I want polynomials such that p0 is equal to p1 is equal to 0. That's all it is. A simple basis on this one is the Lobato basis, which is basically the difference between two shifted Legendre polynomials. If you choose this basis, the matrix A would be the identity again, so you don't have to solve any systems. And if f is nice, and by nice I mean smooth, and the derivatives don't grow exponentially like something that you would see in the Runge phenomenon, then you would expect exponential decay, which is very nice. Let's see an example. Let's take the same function e to the x. I'm sorry, there's something in the chat. H x is equal to, okay, yeah. So someone asked whether x is h01. Yes, it is. Please let me know if there's something in the chat because I cannot see it readily here. Okay, so for example, if I take e to the x, we will see this exponential decay actually. And this is a semi-log plot. So going from degree 5 to 16, you could see that I went from an error of 10 to negative 6 to up to an error of 10 to negative 26, which is extremely small. In the numerical analysis, anything that is less than 10 to negative 16 is basically 0 in double precision arithmetic. Now, what is the issue with the previous spaces? The issue is there is no simple way to make these previous methods work in 2D, 3D if the geometry is complex. Remember that these methods were conforming because they were zero at both endpoints. The geometry in one dimension is very simple. However, they don't work well if the geometry is complex. They would work if we have a square or a cube, and that's what we call spectral methods. Now, the finite element method is a method that combines both previous methods in a certain sense, and it will have a polynomial decay, and then it will have also an exponential decay. And the idea of the finite element method for this Laplace equation or Poisson's equation is to take functions in H01 such that the restriction on each sub interval is a polynomial. Okay. We call those elements. So these subintervals xk plus 1 are what we call the elements. For instance, I can have an interval with 2 elements, and my function could be a linear function here, and another function there, but it is in H01, so it has to be continuous because it's a polynomial. We cannot afford to have a discontinuous function because we are working in H01, okay? And we're also making the condition that phi0 is equal to phi1 is equal to 0. Similarly, we just need a basis. If we have a basis, we can construct the matrix and we're done. An example of a basis on V1H, so 1 is the degree, it means it's piecewise linear, would be the hat functions, okay? Those form a basis. Now, if you look at something like m equals 2, you might have something different. So for example, you can have a hat function that looks like this, where the top is actually in the middle of the interval, okay? So you could do something like that as well. Or maybe you can have something that looks like this, and so on and so forth. And then you just go back to the weak form that we had before. And instead of x, now you have the space VMH, which is our finite element space. And we actually have a theorem about convergence in FEM. The difference, if I assume that my function is smooth enough, the norm of u minus UH is the approximation, in the HI space, so this is an I here, so I'm taking derivatives and computing the error also in the derivatives, is bounded by a constant C times h to the m plus 1 minus I times the semi-norm of U of order m plus 1. Now, instead of going through the proof, which we can talk about how we can prove something like this later on, if you have questions at the end. If I look at this last term here, it shows me that if my U is actually a piecewise polynomial, continuous piecewise polynomial of degree m, this will be 0 and my approximation will be exact. Okay, so that's one thing that we could see. We could see that the approximation worsens with the derivative order. So if instead of the actual approximation you want the derivative of the approximation, you're going to lose some degrees of accuracy. Furthermore, you can notice that if you fix h and you vary m, what happens, you will have an exponential decay. And if you fix m and you vary h, you will have an inversely polynomial decay, something like, or I'm sorry, not inversely polynomial, some polynomial decay, like h squared, h to the third, and so on and so forth. Okay, so that's one of the cool things about the finite element method. And we could play with examples like e to the x that we have done. If you use degree 1, this is a log-log plot. If you use degree 1, you expect something like h squared convergence. And then if you use degree 2 polynomials, you have a cubic convergence, and then you have a fourth order convergence if you use h cubed. Okay. So let's look at this in 2 dimensions. In 2 dimensions, same thing. I have negative Laplacian of u is equal to f, and u is 0 on the boundary. The cool thing about the finite element method is that we can handle a variety of domains. The idea is, instead of subdividing the interval into subintervals, you take what we call a mesh, which consists of a set of elements, and then you divide your domain into these elements, okay? And these guys are polygons. In 2D, we can use triangles. We can use squares or rectangles. And then we can use quadrilaterals. Quads, let's just call them quads, like general quadrilaterals. Now, the reason why triangles are very popular is because the Jacobian of linear transformation that you need to do would be constant, so it helps you avoid doing work on each element. But I could talk about this at the end if you want to. Same thing with rectangles. Quadrilaterals, on the other hand, are bad in that regard, in the sense that the Jacobian would not be constant. For example, a simple mesh on a square would look like this. Now, a mesh on a circle is more interesting because, as you can see, I'm not sure if I could zoom in, it's not very exact, okay? There is some error happening here. And one way to handle this error is through isoparametric elements, or you can just refine the mesh to the point where it's not very important. But for the time being, let's just assume that our domains are polygonal domains and everything's going to be nice. For example, that weird domain that I showed you a few slides ago, we can define a mesh on that domain as well. Now, similarly to u prime, v prime, our weak formulation here would be grad u, grad v is equal to fv on H01. And our finite element space would be the space of polynomials in H01, or piecewise polynomials in H01. And those polynomials are polynomials of 2 variables. And then you do the same thing. You pick a basis, and then when you pick the basis, you have AC is equal to V as a linear system, and then you solve the linear system. So let's see an example. For example, I will use that mesh from that square to solve negative delta U is equal to 1, and I will get this solution. And you can verify it if you want to. You can solve this by hand. And we could do the same thing on this one. We can solve this kind of by hand. It would be more tedious, but we can do it. And we could do the same thing on that domain and solve this equation. Now, because this is the Tassili seminar, I decided to do something tacitly related. So what I did is I take the map of Algeria. I have this domain, and then I have something happening here where the tacity should be. Correct me if I'm wrong. And then I would do the same thing. We define a mesh on this domain, and then we solve the FEM. So if you look at this F, this is the F that I have on the right-hand side. It looks like U, which is something that we usually expect. Okay, so that's the power of finite element. We can do it on practically any domain. We can do the same thing for the heat equation. The heat equation is very similar to the Poisson equation in the sense that it will be UT is equal to delta U with no additional cost. Here's how we do it. Instead of writing UH as the sum of Cj, Pj, we make the Cj's depend on T. Okay. Now this F right here is an initial condition, so it would appear later on in the ODEs. These coefficients Cj would verify that the sum of this phi, pj, c prime, and this c prime, this whole term right here, is coming from the derivative with respect to t of uh. And the right-hand side looks exactly like the right-hand side that we had before, with the exception that it depends on t. And this is what it's going to be, delta u. Okay. There's a negative sign here. So this is negative. No, there's no negative here. Okay, cool. And then this is what I get for my initial condition. So now what I can do, I can write this as MC prime is equal to AC and MC0 is equal to B. So this is just the system of ordinary differential equations, nothing more than that. A couple things about the system. These systems like this would tend to be stiff, so it's usually recommended to use implicit time integrator, but you can solve them with ease usually. Now let's look at something different, and this is where the DG method comes into play. Let's look at something like the transport equation, where we have ut xt plus cux x, and say that c is a constant, positive constant. And u0t is equal to 0, and ux0 is equal to f. If I'm solving this on R, the way this would work is that I start with the wave, and this wave would move to the right. So that's what would happen when I'm solving this. You'll have to pay attention to the fact that we're doing it on the interval 0, 1, and the value at 0 is 0. I cannot impose another one at 1 because the wave is moving to the right. If you try to use the classical finite element method that we have discussed before, try to just multiply by a function v, and then set it equal to 0, and v is space of continuous functions, you'll have some issues, and I can talk more about why this would happen. This, first of all, will not converge in the optimal rate. Okay, for example, the optimal rate for piecewise linear would be h squared. It would not converge to h squared, and so on and so forth. There are other ways around this. For example, there's something called the streamline upwind Petrov-Galerkin, where you would change what the VH looks like. So there are ways around that, but that would lead to some stiff problems. If you have questions about this, we can talk about it later on. Another way to fix this issue is to relax the condition on the space V. Now, we define this V space to be the space of piecewise polynomials from 0 to 1. On each element, it is a polynomial. Also, we can assume that it's 0 at 0. Okay, we can even drop this. Okay, and enforce this one weakly. Now, Q is not continuous. Here's what we will do. We take ut plus ux and multiply it by a test function v and integrate it on ik. Okay, we're not doing it on the whole interval. Our function is discontinuous. We cannot apply integration by parts. Now, you can apply the integration by parts on this term here, and you will pick up some values on the boundary. So basically, you have ut, and then now the derivative moved to the other side, and then you have evaluation at xk plus 1 minus evaluation at xk, what you would get from integration by parts. And the idea of dg is to replace these two values right here by some other well-chosen values. Because remember, UH at xk plus 1, it's not well defined. It has a limit from the right, a limit from the left. So we can choose something in between, maybe the average of the two or some other value at this point. And that's what we call the numerical flux. Okay. If you want to define the numerical flux rigorously, it's basically given a function f of u, and this is what you would see usually in conservation laws. The flux would be a function of the left limit of u and the right limit of u. That it has to satisfy a few conditions. G has to be a Lipschitz continuous function. And then there's a consistency condition that GAA is A. In other words, if the function is continuous at that point, the flux is nothing more than the value of the function there. And also, if it's not increasing in the second component and not decreasing in the first component, we call this a monotone flux. And monotone flux would be stable in a certain sense. There are a variety of fluxes, like the Godunov flux, the Ingwist-Osher flux, and the famous Lax-Friedrichs flux. As it turns out, for the linear case that we were talking about, all of these will be the same thing. So if you use FU is equal to CU like we had, what happens is that the flux would be C times the average minus the absolute value of C times the difference. Okay. We can relax this a little bit and then multiply the second term by a term 1 minus beta. This beta equals 1. I'm sorry. Beta equals 0 would correspond to the upwind flux, and beta equals 1 would correspond to the central flux. We'll see what this means. If I do beta equals 0, the value of the flux will be exactly C times U on the left of X. And here's why this is interesting. If you remember our solution, we said that our solution, let's say that these are two intervals, our solution is moving to the right. So if I want to know what happens on this element, I need to use information from the element next to it. Okay. If I try to just use the central flux, I'm sorry, this is very confusing now. So 0 is the upwind flux and beta equals 1 is the central flux. If I try to use the central flux, I will be using information from this element and from this element, which would lead to a worse approximation because I only need information from the left element. Now, if you write your approximation in terms of a basis, what is interesting about these bases is that these bases can be defined on each element k. Okay, so you give me an element k, that can define a basis on it. I don't have to go through the hat functions. And we can define a local system of ODEs, mck prime minus ack plus a certain matrix f minus. I'm just using minus to know that I'm looking at the left element times ck minus 1 equals 0. Okay, if you want to, you can globalize this and just put all of your ck's in a row and then solve c prime is equal to kct. This is usually easier to write down, but actually for implementation purposes, this is much better because we can handle each element separately, which means that our algorithm would be highly parallelizable. Now let's see why one would want to use DG. First of all, we'll have a high approximation in space. For example, in 1D with a uniform mesh, we'll expect something like OH m plus 1. Okay, that would be our error basically. First order CFL condition. So if you have not seen numerical analysis before, the idea is I'm solving the C prime of t is equal to ACT. Now, if I want to use an explicit time integrator like forward Euler, what I will do CT plus D tilde or delta T. This is going to be CT plus delta T C prime T, which is equal to ACT. And you need delta T times the spectral radius of the matrix A to be less than 1 for your method to be stable. And as it turns out, in DG, what we need delta T times 1 over H to be less than some constant. That's it. For example, in the heat equation, we'll have 1 over H squared, which is bad. But for transport equation, we just need delta T times 1 over H is less than C. And actually, this will be roughly 2 over M plus 1 in 1D and also in 2D with uniform meshes. This is still an open problem actually for general meshes. Also, it's very flexible. You can use different spaces on each element. You can use degree 1 on one element, and on the neighboring one, you can use degree 7 if you want to. And sometimes that's very desirable, especially if our function is smooth in one region and coarse in other regions. Other things, it's highly parallelizable. You can do it on multiple CPUs at the same time, up to millions of CPUs. It's HP adaptive. What that means is I can keep varying the H and the P to gain a better approximation. So whenever the solution is not smooth, I would use smaller H's, and whenever the solution is smooth, I would use higher degrees. And it handles these nonlinear conservation laws very, very well. And you can generalize it to 2-3 dimensions. The matrix assembly is very simple. You can use a basis that makes the mass matrix, the M matrix that we talked about, make it the identity. And there are superconvergence properties. This DG solution would approximate the solution better at certain points. Now we could do the same thing with systems. If I had UT plus AUX is equal to 0, with some boundary conditions, those are kind of, you can think of those are periodic boundary conditions, but with inflow. This if matrix A is assumed to be diagonalizable to real eigenvalues. And A plus and A minus are defined in the following way. If you take A and you take the eigen decomposition of A plus or A minus would be 1/2 of this Q times lambda plus or minus the absolute value of lambda. So basically A plus has only the positive eigenvalues, A minus has only the negative eigenvalues, okay? That's all it is. You can do the same thing with the DG formulation. You integrate by parts right here, and you pick up some terms here, and then you have a flux. Now the flux, the upwind flux in this case would be A plus, you multiply by the value on the left, plus A minus, you multiply by the value on the right. Well, number one, the energy is decreasing actually in something like this. So if you take the energy to be the L2 norm squared, then it will be decreasing. And actually, the way it would decrease, it will depend on the jumps. So this double bracket is basically the jump of the function across the elements. So if your approximation stays continuous, you will have conservation. And dissipation is not a property of the solution itself, U. U conserves E, but we want to have some dissipation to maintain stability of our linear solvers. And for convergence, if I assume that my U is smooth enough, unfortunately, you could see here that we are assuming that U is in HK plus 2, not HK plus 1 like the Laplace equation, we will have optimal convergence rate in space, which is HM plus 1. And that's it. Questions?